Alright children, again I'll do the continuation of same explanation. I'm about to complete this application. Okay, so in the last video that we have discussed up to this relation, the electric flux due to two end of the cylindrical Gaussian surface is equals to 2EA, right? But we need to find the electric flux even for this curved surface, So for this curved surface, I take also a very small area element, and that area element is what? dA. You take anywhere on the curved surface. Suppose if I take the area element, small area element dA. So what is the area vector? Outward normal, this side. But at the same point, your field due to this area will be this side only. So look at the direction. The electric field and the area vector are perpendicular to each other. What is the angle between them? Theta equals 90 degree. And when theta is 90 degree, remember this, cos 90 degree equals to 0, because we are measuring the flux, and flux is expressed in terms of what? Cos theta. And if cos 90 is 0, means the flux will be 0, which means the electric flux produced by this plane sheet of charge of area A, okay, on the curved surface will be what? 0. So there will be no flux. Okay, there will be no flux. Okay, that's why the electric flux for curved surface of cylinder is what? 0, as E and dA are perpendicular to each other. Okay, everywhere on the what surface? Curved surface. That's why the flux on the curved surface is 0. So we have flux only on the what? Two end of the cylinder. So that what is the net flux or the total electric flux for the entire cylindrical Gaussian surface? That is phi is also equals to 2EA. So we have already made equation 1. That is the electric flux due to two end, due to the plane surface at two end of the cross sections, two end of cylindrical Gaussian surface, and that is only the net flux due to the entire cylindrical surface. But you know, according to Gauss theorem, flux is also measured by Q by epsilon naught, where Q is the net charge enclosed by the Gaussian cylindrical surface or Gaussian cylinder. That means these two flux are equal. So if these two flux are equal, means I can write phi also as Q by epsilon naught equals to 2EA. Q by epsilon naught equals to 2E what? A. Which means Q by epsilon naught equals to 2EA, then 2E, or we can also write this as 2EA equals to Q by what? Epsilon naught. Which means from this relation, if I make E as the subject, then E equals to Q by 2A and AU, taking the denominators, it will be E equals to Q by 2AE. But you know what is Q by A? Sigma, that is surface charge density. That's why E equals to sigma by 2 epsilon naught. So if you look at this expression, the electric field due to plane sheet of charge depends upon surface charge density, okay, in a given medium. More the surface charge density, more the electric field. But electric field is independent on the distance. So remember this, electric field is independent on the distance from the plane sheet of charge. Means whether you calculate the field very close to the charge or away from the charge, the magnitude of field remains same. Okay, so it means that the electric field is same at all points due to any plane sheet of charge. So that is only for the plane sheet of charge, but the plane sheet of charge of any area, okay, the electric field produced by plane sheet of charge of any area is independent on the distance, that is R, and it means same everywhere on both sides of the plane sheet of charge. Okay, so this is one of the important conclusion that we can draw. But I'll tell you, there is an important note, you need to write it down. Electric field E at any point, say P and P dash, is directed away from the what charge? Positive charge. If the charge is positive, then the field is always directed away from the charge. But if the plane sheet of charge is negative, then the field is always directed towards the sheet of charge. Okay, that means the direction of field determined by the nature of the charge. So this explains the application of Gauss theorem.